Good evening. We'll just wait one more minute for people to join in and then we'll start. Okay, so now we can start. The last classes we have revised and discussed about a lot of questions, and we have almost covered all kinds of spectroscopies. There are a few questions which we have left out, and we will be discussing a little more about them today. And because those questions deal with topics that have also been missed out during the classes, so we can touch upon these finer points now. So the first topic that I will be touching upon today will be the Born-Oppenheimer approximation and Frank-Condon principle. So these are all related to the fundamentals of the spectroscopies. So let us just have a look at them. So we're going to talk about the Born-Oppenheimer approximation. So, in a molecule, whenever we have the kinetic energy, so the kinetic energy means motion. Okay, so what is the motion? The electrons can move and the nuclei can also move. So, if the kinetic energy is represented by T, and let the contributions from the motions of the electrons and the nuclei be Te and Tn respectively. So similarly, the potential energy can also consist of two terms, that is VEE and VNN, and these can be due to the Coulombic repulsion between the electron. Electron-electron repulsion will be represented by VEE, and VNN will be the repulsion between the nuclei. Similarly, these two repulsive terms will also have a complementary attractive term, that is VEN, giving the attractive forces between the electrons and the nuclei. So if we were to completely write the Schrodinger's equation, okay, Schrodinger's equation represents the complete state of the system and also gives the energy. So if we were to write the complete Hamiltonian, H is representative of the Hamiltonian, and this is usually the if you have read in your MSc classes, you must have read the Schrodinger equation. So He psi E is equal to E psi E, where psi is the wave function, E is the energy, and H is the Hamiltonian. So we can write the Hamiltonian as a mixture of all these terms. So both the contributions from kinetic energy and the three contributions from potential energy, they can be added up to form the Hamiltonian. If the nuclei are fixed, then they will not have any kinetic energy, so the Tn term can be zero. and VNN will be a constant. Okay, VNN will be a constant. So nuclear attractive forces, they will be constant for fixed nuclei. So there is a set of these electronic wave functions which will satisfy the Schrodinger equation, and ultimately this the first equation condenses to TE, VEE, and VAN. Now, now HE, that is a Hamiltonian, depends on the nuclear coordinates because of the VEN term. Also, wave function and energy will also be dependent on the nuclear coordinates. But in order to simplify this particular problem, to solve the Schrodinger equation, Born and Oppenheimer, they proposed an approximation in 1927 where it was assumed that whenever the nuclei are vibrating, they are moving so slowly compared with the electrons that the wave function and the energy, they will involve the nuclear coordinates as parameters only. Okay, they will involve the nuclear coordinates as parameters only, and so the result for a diatomic molecule will be a curve of potential energy against internuclear distance. Okay, the result for a diatomic molecule will be a curve of potential energy against internuclear distance, or the displacement from equilibrium, and this can be drawn for a particular electronic state in which the kinetic energy of the electrons and the electron-electron repulsions will be constant. This is known as your Born-Oppenheimer approximation. So this is drawn from the approximation that the nuclear coordinates are moving very slowly as compared to the electrons. So the total wave function, they can be factorized as a product of psi e and psi n, where psi e is the function of nuclear coordinates as well as the electron coordinates. So capital Q is for nuclear coordinates and small q is for electron coordinates. So the total wave function can be factorized like this. Next, we come to Frank-Condon principle. So what is a Frank-Condon principle? So let's discuss the history of the principle and how it came about. In 1925, before the Schrodinger equation was developed, Frank put forward qualitative arguments to explain the various types of intensity distributions that are found in vibronic transitions. So, this is related to electronic spectroscopy and has implications in fluorescence spectroscopy as well. We will see that. His conclusions were based on the fact that the electronic transition in a molecule takes place much more rapidly than the vibrational motion of the nuclei, such that the instantaneous internuclear distance and the velocity of the nuclei can be considered to remain unchanged during the electronic transition. Now, this also formed a basis for the formulation of the Born-Oppenheimer approximation. Okay, although it referred to the main principle will be that the electronic transition is taking place more rapidly than the vibrational motion of the nuclei, here also you will see that the movement of the nuclei or the velocity of the nuclei or the changing internuclear distance, they are kept as constant, which means that बॉर्न ओपेनहेमर में भी जो बोला जा रहा था कि न्यूक्लियर आर मूविंग वेरी स्लोली, दिस इज ऑल्सो फॉर्मिंग द सेम कंक्लूजन and they are considered to remain unchanged during the electronic transition. So in the diagrams that show the potential energy curve of the two electronic states of the molecule, the transition must be represented by vertical lines. Okay, the transition must be represented by vertical lines, and these vertical lines will be the most probable or most intense transition. So if we have these potential energy diagrams, so whenever we have a vertical, so Frank-Condon principle always works in the vertical direction. Okay, it always works in the vertical direction. So here, so here in both the cases, okay, here in both the cases from A to B, okay, from A to B, this will be the most probable. Okay, this will be the most probable cases. So it will just be vertical. If it aligns a little, like A to C is also possible. Okay, A to C is also possible, but A to B will be most preferred because it is the most intense and most vertical line. So any vertical transition will be the most probable in a particular system. Also, another factor to be considered is the distribution of the probability density. So from the quantum mechanical concepts, we know that the probability density is psi square. Okay, and psi square varies in various vibrational level. You have different kinds of psi square. So distribution of the psi square in various vibrational level of each electronic states is to be considered. Now, greater the values of the probability density at particular values of internuclear distance in a vibrational level, greater is the probability that the nuclei will be found at that distance apart. Okay, so it is evident that psi square is at a maximum at the midpoint of the V is equal to 0 level and near the turning points of the higher energy levels. So here you will find the psi square to be the highest. Okay, this you will find the psi square to be highest at the midpoints and also near the turning points of the higher energy levels. So at the V is equal to 0 is the psi 0 square. So इसके midpoint में तुम्हारा probability density will be the highest, and as you go high, turning points of the higher energy levels means this, whenever there is a turning point at the higher peaks, you will find that the psi 0 square is again maximum. So the Frank-Condon principle is also stated as the most probable vibrational transitions are those in which one of the two turning points of a vibrational level of one electronic state lies at approximately the same internuclear distance as one of the two turning points of the level of other electronic states, except in case of V is equal to 0 level, for which the midpoint rather than the turning point must be substituted. So you can also write this as an extended form of the Frank-Condon principle. Now, you do not require the quantum formulation of Frank-Condon principle, but let us still look into what they are saying. So you can have an idea and you can write if you want. So in quantum mechanics, intensity of a spectroscopic transition between two states of total wave function psi dash and psi dash dash is dependent on the square of the transition moment. So if you're defining this corresponding transition moment, we can define it as an integral of psi dash star m and psi dash dash, where they are operating on the electric dipole moment m, which has components sigma ei xi. So if we are ignoring the rotation and applying the Born-Oppenheimer approximation, then psi will be a combination of electronic and vibrational wave function. Also, the dipole moment can also be written in terms of the electric and nuclear components. So we can combine this both and we will get two terms like this. Okay, we will get two terms like this. And the second integral here, the nuclear dipole moment mn, it will be independent of the coordinates of the electrons. And the second integral, they can be written in this manner. Okay, in this manner, and this will be 0 because here you are taking the electronic wave function which belong to different electronic states of a molecule. They will be orthogonal. So you just go back to your quantum mechanical principles and you will understand. So this particular wave function will be 0. So r will be equal to just the first term. Okay, r will be equal to just the first term. And then thereby it can be approximate. If you take re out, as the variation of re with r is slow, and they can be approximated as re bar, and re bar will be the average electronic transition moment, and it will govern the intensity of the band systems as a whole. Now, if we are considering the integral part, then this particular integral part, and if you're squaring it, that will be the Frank-Condon factor. We can tell that re bar with q here, this particular factor, if we are squaring, we can get the relative intensities of the various bands of the system, and this is known as the Frank-Condon factor. Now, these are quite complicated concepts, so you can take this PDF and you can read this for advanced reading. But for your syllabus, you can just read up to this point about the basic definition and the diagrams for Born-Oppenheimer approximation as well as the Frank-Condon principle. So you have to read only till this much. Okay, till page 7, I will be giving this PDF. So this is all for our first concept that we discussed today. That is the Frank-Condon principle and the Born-Oppenheimer approximation. This has come up in various questions. Today we'll just go through the questions that have come up from this portion. The next portion that we will discuss is from fluorescence. We will again go back to the Frank-Condon principle and start from there and see what it has for fluorescence, what kind of concepts it has for fluorescence. In fluorimetry and phosphorimetry, we have dealt with the applications, the instrumentation, the Jablonski diagram, okay, the sources and everything that we have dealt with. We have missed out on two concepts, that is quantum yield and fluorescence quenching. So we will be looking into these as well. So just wait. So we are back to the Frank-Condon principle, and let us move from there. So just a revision. So the Frank-Condon principle states that because the nuclei are much more massive than the electrons, the electronic transition can take place more faster than the nuclei can respond. And so this results in the most likely transition being the one when the internuclear distance at the turning point of the excited state has the same value as the equilibrium position in the ground state. So the most likely transition is often called the vertical transition. And quantum mechanically, the vertical transition is determined by computing the overlap integral of the ground state and the excited state. Higher the value of the integral, more intense the transition between the two states, and the highest value indicates the vertical transition. So what you're going to do is you're going to combine the two slides, that one and this particular explanation, when you're going to write about Frank-Condon principle. Here they have just stated what the quantum mechanical explanation is, and you don't have to do much of the calculations or the equations. So you just can state this. Okay, you can just state this. So here we are coming to fluorescence now. So fluorescence, this is the absorption and the fluorescence spectrum of quinine sulfate. Now, how can the intensities of the fluorescence spectra be connected to the Frank-Condon principle? Now, this is the application part. How can the intensities of the fluorescence spectra be connected to the Frank-Condon principle? Now, we have already discussed earlier also that they are that the integrals are controlling the band intensities. So here also it is written that the intensity of a transition is proportional to the overlap integral of the wave function for the two states, and it depends on the transition dipole moment. Okay, it depends on the transition dipole moment. So we have covered Jablonski diagram already. Now we come to fluorescence quenching. We will again do this fluorescence quenching with a different material, but first let me go through this one. So what is fluorescence quenching? Fluorescence quenching is a process of relaxation which occurs without emission of a photon. Okay, it is a process of relaxation which occurs without emission of a photon, and the excess energy can be converted in the translational, rotational, or vibrational energy of a different molecule, atom, or ion, which then undergoes relaxation itself, or in the case of a gain in translation energy, the temperature is raised, and quenching is a second order reaction. So this can be a description like table 5, this particular thing you just see. Okay, so we can have different kinds of processes: absorption, fluorescence, non-radiative decay, and quenching. So in absorption, what is happening? That a molecule is absorbing a photon and then it becomes activated. In fluorescence, that activated or the excited molecule emits another photon and comes back to the ground state. In non-radiative decay, it just comes back to the original state without emitting any photon, or there is a non-emissive kind of a decay. And in quenching, what happens that after absorption, even if the molecule is going to a higher excited state, there is some substance that is being added or some kind of phenomena that is occurring, which leads it to come back to the original state along with the quencher. Okay, this is what is happening with the quencher, and we will also discuss this in detail. Next is the fluorescence quantum yield. Okay, what is the fluorescence quantum yield? So just write this particular ratio. This you will also find in your study material. So for fluorescence quantum yield is the ratio between the absorbed photons and the emitted photons. It is the ratio between absorbed photons and the emitted photons. So quantum yield is equal to molecules fluorescing per unit of time and volume, molecules fluorescing per unit of time and volume divided by photons absorbed per unit of time and volume. Molecules fluorescing per unit of time and volume divided by photons absorbed per unit of time and volume. So suppose the molecules fluorescing are given by this particular equation, this particular expression, and the photons absorbed, they can be expressed as the molecules. And when these molecules, when they absorb a photon, they can be represented by K absorbent into concentration of M. Now we can write a steady state approximation for continuous irradiation. So it will be minus d m star by dt can be equal to the molecules that are fluorescence, the non-radiative decay, the quenchers, and the molecules that have absorbed the photons. Again, I'm repeating, this expression is for molecules that have fluoresced. This is for non-radiative decay. This one is for quenching, and this particular one is for the absorbed photonic molecules, and they can be rearranged. Okay, they can be rearranged, and this is equal to 0. For steady state approximation, हमेशा ये वाले equations 0 होते हैं. So m star, if we are taking common, this will be reduced to K absorbed into concentration of M by this particular terms. Okay, the addition of this particular terms. So they can be convenient. So this here means that the quantum yield, that is phi f, capital phi f, is conveniently expressed through the rate constants for emission. Okay, this expression is for emission. This is the rate constant for emission. Then non-radiative decay ke liye rate constant is KNR, and the quenching rate constant, that is KQ. And it is also equal to phi f. Okay, the expression also reduces to this particular format. So these two expressions are important. Okay, these two expressions will be important. So once we get m star, then we can substitute in the original phi f, and we will be able to get this particular expression. Now the question comes, when does phi f become unity? When does phi f become unity? If there is no quencher in the system, if there is no quencher in the system, or the rate of emission is much higher than the rate of non-radiative decay, okay, if the rate of emission is much higher than the rate of non-radiative decay, then it will be unity. So now carefully look at phi f is equal to this particular expression. Now if there is no quencher in the system, the KQ term becomes 0. Okay, this will become 0. Also, if the rate of emission is much higher than the rate of non-radiative decay, then KNR will be very, very small and it can be negligible. So what will we be left with? The rate constant for emission divided by rate constant for emission, and that will be unity. So when does phi f become unity? If there is no quencher in the system and the rate of emission is much higher than the rate of non-radiative decay. I hope that is clear. Now, how is the lifetime defined? So what is the lifetime of the fluorescence spectra? Okay, what is the lifetime of the excited state? Now suppose a molecule is there, and it has been excited to a particular state, that is m star, and then it is returning back to its original state with the emission. So the lifetime is defined by the expression tau. Okay, it is expression tau, and the lifetime of the excited state is the time the average molecule stays in the excited state before returning to the ground state. Okay, so the lifetime of the excited state is the time the average molecule stays in the excited state before it returns to the ground state. Now, this particular process has a first order characteristic. Okay, this process has a first order characteristic. What order was quenching? Quenching was second order. Okay, but this particular process has first order characteristic, and the concentration of the excited state molecules can be expressed by m star is equal to m star 0 e to the power minus kt. Now, this one, if you've read about chemical kinetics, this is very reminiscent about chemical kinetics. You must have learnt about nuclear decay as well. So, this expression can be gained from the knowledge of chemical kinetics and nuclear decay. So, you can just go through if you don't know this particular format yet. So, m star is equal to m star initial concentration of m star into e to the power minus kt. Now, to get the lifetime, now one has to apply the definition. So, tau is equal to 1 by m star 0, 0 to infinity m star into dt. And that will be equal to 0 to infinity e to the power minus kt into dt. And ultimately, we get 1 by k. So, k is a rate constant. So, natural lifetime means lifetime for an ideal fluorescing system is the inverse of the rate constant of emission. Okay, it is the inverse of the rate constant of emission, and the k that we are defining is k is equal to rate constant of non-radiative decay plus rate constant of emission. And in an ideal case, the rate constant for the non-radiative decay is usually equal to 0. So tau n is equal to 1 by, so it is a reciprocal of the rate constant of emission. But this is just for the ideal system. If it is for the real system, then there is non-radiative decay and there can also be quenching. Okay, there can also be quenching. Now, non-radiative decay can also include intersystem crossings. Okay, they can also include intersystem crossing. So tau can be given as 1 by rate constants, all the rate constants, that is rate constant of emission plus rate constant of non-radiative decay plus rate constant of the quenching into quencher concentration. Now, what is the Stern-Volmer equation and how would you construct the Stern-Volmer diagram? Now, this is also frequently coming in exams. So, lifetime, quenching, Frank-Condon principle, Stern-Volmer equation, all of this is coming as questions in the exam. So, you can just revise from the study material as well. So, let us discuss here as well. So if we are forming the ratio of the quantum yield in absence of the quencher to the quantum yield if there is a quencher, so let us take phi 0 as the quantum yield in absence of a quencher. So the rate constant will be just that of the emission. Okay. So rate constant of emission by rate constant of emission plus rate constant of non-radiative decay. That is your phi 0. And if you're taking phi, if there's a quencher phi, then normal equation that we saw here, phi by, so that rate constant of emission divided by all the rate constants, that is rate constant of emission plus knr plus kq into q. So if you're dividing it, then what is happening, this particular term and this particular term and this particular term is getting cancelled. Okay, this particular terms are getting cancelled. So finally you can do this as phi 0 by phi is equal to phi plus knr by phi plus knr plus kq into q by this particular term plus knr. Now this reduces to 1. Okay, this reduces to 1. And if we are constructing the terms in a particular manner, then if the quencher concentration is 0, okay, if the quencher concentration is 0, the lifetime will be given by 1 by rate constant of emission plus rate constant of non-radiative decay. Now here we can write this particular term as phi 0 by phi plus is equal to 1. Okay, 1 plus tau into f into kq into q. Tau into f into kq into q, and this will be equal to 1 plus this entire thing, tau f into kq, we can write as ksv. Okay, we can write this as ksv into quencher. So this will be your Stern-Volmer equation. Okay, this will be your Stern-Volmer equation. And this phi 0 by phi, they you can also represent that as, you can also represent that as I 0 by I, or the intensities. You can also represent that in terms of intensities. So the, what is the Stern-Volmer constant? This is the KSV, and it is equal to the lifetime when the quencher concentration is not there, lifetime into the rate constant for the quencher. Okay, rate constant for quenching into lifetime when the quencher is not there. So here you get I 0 by I or phi 0 by phi, and you can construct the Stern-Volmer plots. And for the Stern-Volmer plot, what will be the slope? The slope will be, the slope will be equal to the Stern-Volmer constant only. So if we are taking y is equal to mx plus c, the intercept will be 1. And if you are taking it against the quencher concentration, okay, if you are taking it against the quencher concentration, then the slope of the Stern-Volmer plot will be KSV, or the Stern-Volmer constant. So for various concentrations versus phi 0 by phi or I 0 by I, you can see the different constructs of the Stern-Volmer plots. So this one we will stop here, and we will move to another material where quenching is explained in detail. One second. Okay, so we have talked about when can quantum yield become 1, and we have said that when the quenching concentration is 0, and uh, we have already discussed some conditions relating to when the quantum yield can be 1. But why can't quantum yield become 1 for most practical cases? Because a lot of energy is lost in vibrational transition and collision with the solvent, and only a part of the light absorbed is emitted. Also, quenching of the fluorescence cannot be just negated or seen to be in the ideal circumstances, because there might be also some impurity in the solution, some kind of a foreign molecule which is acting as a quencher. For example, even if there is there is some kind of a structural rearrangement in the molecule which drives the fluorophore to a conformation where it is in the vicinity of a quencher, and that quencher can be an amino acid residue, it can be something in the solution, or it can be also a disulfide bond, it can interfere with the fluorescence. So you cannot say that the quenching concentration should be absolutely 0, because any kind of a impurity, any kind of a rearrangement can also lead to quenching. Also, the fluorescence intensity can decrease due to the transfer of the emitted energy to some other chromophore which absorbs that energy. This is also called fret. Okay, this is also called fret, and we will also look at that. So here is the experimental setup. Okay, here is the experimental setup for the emission spectra and the excitation spectra. So two kinds of spectra can be measured for fluorescence spectra, that is emission, and the excitation spectra. So the emission spectrum, here the excitation wavelength is kept constant, and the intensity is measured as the function of wavelength. That is, the spectrum of emitted light is determined. The excitation spectrum, the fluorescence intensity at a particular fixed wavelength is measured as a function of the excitation wavelength. Now, what can be the effect of solvent on the fluorescence spectra? What attributes of the solvent can have an effect on the fluorescence spectra? You can change the polarity of the solvent and the viscosity, and the fluorescence spectra will have an effect. If the rate of solvent relaxation changes, then also you can expect fluorescence spectra changes. Rigidity of the local environment, probe interactions, conformational changes of the probe can affect the fluorescence spectra. Also, proton transfer and excited state reaction as well as internal charge transfers can also affect the fluorescence spectra. Here you can see the diagrammatic representation of how the solvent can affect the fluorophores. So typically in a fluorophore, it has a larger dipole moment in the excited state than the ground state. But if you have a solvent, then it can shift the emission to a lower energy because the excited state is stabilized by the polar solvent molecule. So when the solvent polarity is increased, the effect becomes larger. So here you can see that in a particular molecule named as prodan, the emission spectra is shifting in different kinds of solvent. From different concentration of heptane and water, the fluorescence intensity is also shifting. And here you can see that whenever the solvent polarity is increasing, it leads to a larger red shift. So it's a shift towards longer wavelengths when the water is being increasingly used. Similarly, at different temperatures also, the fluorescence spectra can be affected. Here, taking the same molecule at two different temperatures, we are measuring 100 and 300. So whenever there's a decrease of temperature from 300 to 100, there is an increase of viscosity. So there will be a increasing fluorescence contributions of the non-relaxed states. So more and more fluorescence contributions will be taking place from non-relaxed states, and you will get a blue shift or a shift towards shorter wavelengths. Now, can fluorescence be taken as a pH indicator? Yes, it can be taken as a pH indicator. And there's an equilibrium between the protonated and the deprotonated form of the fluorophores in many cases, which can differ in the spectral properties. They can even measure the pH inside of cells and cellular compartments, and many pH sensitive dyes can be genetically encoded. So you can also see some examples relating to this. Now, quenching, when we say, we need to see what kinds of processes are referred to as quenching. So, anything that decreases the fluorescence intensity of a sample is quenching. And mainly, whenever we are saying a quencher, we are referring to, immediately in our mind, we are thinking some foreign substances being added, which is leading to the decrease of the intensity, but it is not always so, because a variety of molecular associations can also result in quenching. And these include excited state reactions, molecular rearrangements, energy transfer, ground state complex formation, and collisional quenching. Okay, so many kinds of reactions can lead to quenching: excited state reactions, molecular rearrangements, energy transfer, ground state complex formation, and collisional quenching. Also, a wide variety of substances, they act as quenchers of fluorescence. For instance, quenching by oxygen is due to the paramagnetic nature of oxygen, which causes the fluorophore to undergo intersystem crossing to the triplet state, thus reducing the intensity of the fluorescence. So the immediate emission does not occur, and that might be a time decay. Collisional quenching is when the excited fluorophore experiences contact with some atom or molecule, and this can facilitate non-radiative transitions to the ground state. Collisional quenching can include oxygen, like we've discussed, oxygen, iodide molecules can be there, cesium plus molecules can be there, iodide ions, cesium ions, and acrylamide. Okay, oxygen, common quenchers include oxygen, iodide ions, cesium plus ions, and acrylamide. And in the simplest case of collisional quenching, the following relation called the Stern-Volmer equation holds. We have just seen this: phi 0 by phi, or I 0 by I, is equal to 1 plus KSV into quencher concentration. And I 0 by I or phi 0 by phi can be plotted against quencher concentration. The intercept will be 1 and the slope will be the Stern-Volmer constant, or KSV. We have seen the origin of this particular equation just now. We have seen the derivation just now. And there can be different kinds of quenching, like static quenching, okay, or combined static and dynamic quenching. You can just remember this particular plot. Okay, this can be a static quenching and the exponential one can be your dynamic quenching. So just remember this diagram. Do not need to go into the details. Now, why do non-linear Stern-Volmer plots why they can be happening? Because suppose some of the fluorophores are less accessible than others. Suppose you have a folded protein and there you have multiple tryptophan residues. So some of the residues will be more accessible and some of the residues will be less accessible to the quenchers in the solvent. So in the environment itself, it can differentiate between the fluorophores which are less accessible and some which are more accessible. So in these kind of extreme cases, if you are plotting a Stern-Volmer plot, that will not be linear. Okay, that will not be linear. It will be a curve like this reaching a plateau. So I0 by I versus Q, it will not have an intercept or anything, will not be a linear plot. It will be a curved plot. Okay, it will be a non-linear Stern-Volmer plot where the quencher is not able to access all the fluorophores in the system equally. Now we have talked about FRET. So you just remember the concept very briefly. What is FRET? FRET is known as Foster's Resonance Energy Transfer. Foster's Resonance Energy Transfer, or FRET. It is a non-radiative process. And here what is happening is the fluorescence emission from the donor atom is being absorbed by the acceptor. And the emission spectrum of the donor is the and the absorption spectrum of the acceptor, they have a spectral overlap. It is dependent on the distance between the donor and the acceptor. So as soon as the donor is emitting, the acceptor is absorbing it and there is a spectral overlap. So this is the basic concept of FRET. This is the energy transfer efficiency. KET is the energy transfer and Ki is for all the deactivation processes. And experimentally, if we are trying to calculate the energy transfer efficiency for FRET, then you have to calculate the fluorescence lifetimes or intensities of the donor that is determined in absence and presence of the acceptor. So donor, acceptor, and only donor. And what about the distance dependency? Because the donor and acceptor distance is very important. So if R is the distance that is separating the center of the donor and acceptor of fluorophores, and R0 is the Forster radius, then 1 by E minus 1 to the power 1 by 6 R0 is the equation for the distance separating the center of the donor and acceptor fluorophores. And the efficiency varies with the inverse sixth power of the distance. So if you are asked to plot the difference between the graph between efficiency of transfer and distance, you can follow this particular graph. So this is a summary of FRET and what it can do. It is usually ideal for measuring the distances between 10 to 80 angstroms, which is relevant to the biological system. The efficiency and the rate of transfer we have already dealt with. And unique locations of the donor and acceptor in the protein molecule can allow one to monitor the conformation of the protein with respect to the position of the donor and acceptor. So it is a spectroscopic ruler, which means that in various kinds of complicated protein molecules where we do not know where the positions of the donor and acceptors are there, if we are using FRET, we can calculate the location of the donor and acceptor and we can see the conformation of the proton that way. So this is how the FRET spectrum looks like. In absence of the acceptor, the donor emission is enhanced. Whenever there's an acceptor, before the donor emission is completed, the acceptor is absorbing it. So that is why the emission level is decreased. Okay. And finally, there is a fluorescence emission of the acceptor upon excitation of the donor at a longer wavelength. There's also the application part. The phenylalanine aniline amino acid has a low fluorescence in the in protein because of its energy transfer to tyrosine and tryptophan, and this energy transfer is also reason why the tyrosine fluorescence is not observed in proteins which contains both tryptophan and tyrosine, because the energy transfer can also occur from tyrosine to tryptophan in the compact native state. So that is why we can see that the applications of FRET in protein conformational spectra is quite high. So you can explain the FRET through this diagram as well. We have already talked about lifetimes, and the applications are this. They can be independent of the probe concentration. They can be used for cellular imaging. Okay, they can be used for cellular imaging. So lots of applications are there. You can check from this particular PDF. I'll be giving it to you. Now, the applications of fluorescence lifetime is that it is useful for elucidating different kinds of interactions within molecules. The size and the shape also changes in the solvent like viscosity, pH, polarity, and solvation. The kinetic and dynamic rates, the different kinds of distances, and also the resolution of the molecular mixtures and their compositions. Okay, you can also determine the compositions. And we have already also discussed about the decay of the excited state of a molecule to the ground state. So these are all advanced topics. You do not need this much. So till this much, you will be reading, revising from this PDF till slide 40. So I'll be sharing this one shortly with you. So let us take a short break, and we will be back. We'll be discussing some questions, and we will be also touching upon atomic emission spectroscopy. I think there was some confusion someone had written between AAS and AES and flame photometry. So we'll be briefly discussing atomic emission spectra, as well as a little bit of flame photometry we'll be revising. And another question that is frequently coming is ICP-AES. So we will be discussing that as well. So let us take a short break. I'll be sharing this particular PDF for the fluorescence spectra here. And the other ones also I'll be sharing in a while. So just take a break and revise through this. I'll be back. Okay, so let us get back to it. Write some questions on the portions that we have just discussed. Also, on the portion that we will be discussing, that is atomic emission spectra. So, first question, right? State Frank Condon principle, state Frank Condon principle, and explain its implications. State Frank Condon principle and explain its implications. Briefly discuss the non-radiative deactivation. Briefly discuss the non-radiative deactivation of the excited state of a molecule. State Frank Condon principle and explain its implications. Briefly discuss the non-radiative deactivation of excited state of molecule. Then write define quantum yield. Define quantum yield with help of mathematical expression. Define quantum yield with help of mathematical expression. Describe principle of atomic emission spectrometry. Describe principle of atomic emission spectrometry. Discuss role of plasma sources in AES. Describe principle of atomic emission spectrometry. Discuss role of plasma sources in AES. Draw a schematic layout of different components of an ICP AES spectrometer. Draw a schematic layout of different components of an ICP AES spectrometer. Discuss role of monochromators. Discuss role of monochromators. Then write describe in brief fluorescence quenching. Describe in brief fluorescence quenching and write the Stern-Volmer equation. Describe in brief fluorescence quenching and write the Stern-Volmer equation. What type of atoms and molecules show quenching? What types of atoms and molecules show quenching? Again, there was a question, same kind of question for Frank Condon. State Frank Condon principle, give the significance. So you can write in implications, significance, it's all the same thing. Basic principle of atomic emission spectroscopy, again, as a question it has been asked. Differentiation between AAS and AES, atomic absorption and atomic emission spectra. That also is a question. Define quantum yield has come almost in every year. Define quantum yield. Give mathematical expression explaining all the terms. Mathematical expression explaining all the terms. Advantages of ICP AES. Special advantages of ICP AES. Again, give a tick mark for different components of ICP AES spectrometer. That also give tick mark. Okay, yeah. So I took a pause to just share some links in case some of you leave, because some people are leaving before the class ends. So just I'm sharing some links so that you have all the materials. Okay. So we are continuing with this. So again, compare AAS and AES in terms of advantages and disadvantages. AAS and AES in terms of advantages and disadvantages. That one has come. Then again, define and differentiate AAS and AES. So this define and differentiate is coming very frequently. So you take care of this. Then relating to the components of the spectrophotometries, you have to take care of the sources, the monochromators, what kind of sources are being used. For example, for AES plasma source, why is it so important? That kind of question is coming. Plasma source. Okay. Why plasma source is coming? So you take care of that. Place a tick mark for spectral interferences again. Spectral interferences, that you also take care. Then ICP torch. Okay. Right. Discuss the rationale behind choice of argon used as plasma gas. Discuss the rationale behind choice of argon used as plasma gas. Show the temperature profile of a typical ICP torch. Show the temperature profile of a typical ICP torch. Then discuss the analytical methodology in ICP-AES. Discuss the analytical methodology in ICP-AES with emphasis on quantitative analysis. Then again, same kind of questions are repeated for fluorescence. Explain fluorescence quenching. Give Stern-Volmer equation. Which type of atoms or molecules show quenching? So very easy. We have just discussed. So you can place a tick mark there as well. Then not much else is coming. Just for fluorescence, that particular thing was that in multiple years they have asked for this kind of, again, this kind of things are being asked. Explain fluorescence quenching with help of example. So essentially the same thing, not much too complicated, but a little wording is changed and it is given. Spectral interferences, like I told you, spectral causes of spectral interferences in ICP AES method. So if you know one type of spectral interferences also, you can write something there. So in another 2 years also, I'm seeing that fluorescence quenching, Stern-Volmer equation, quantum yield. This is coming for 5 marks. Explain inductively coupled plasma. Now this is related to your AES. Okay, ICP AES. Explain inductively coupled plasma. And then monochromators of high resolution. Monochromators of high resolution are found in ICP-AE spectrometers. Monochromators of high resolution are found in ICP-AE spectrometers, but not in flame AA spectrometers. Monochromators of high resolution are found in ICP-AE spectrometers, but not in flame AA spectrometers. Justify. Then I think these are all repeat questions which I'm seeing. Again, the question is written, but just different wording. So just listen to this one. The ICP torches use argon as plasma gas. What makes argon a good choice for the purpose? ICP torches use argon as plasma gas. What makes argon a good choice for the purpose? Neat diagram of ICP torch and explain working of various components. Neat diagram of ICP torch and working of various components. Instrumental setup of ICP AES, again repeated. So I think we are done with the questions. These are all the questions that have come from Frank Condon and Born Oppenheimer, fluorescence, and AES. We have just one topic to. Sorry, it got muted. So we have just one topic to cover right now, that is AES. We have just briefly touched upon that, but we'll go through it again, and we will see the ICP AES part because it is coming frequently in the exams. So we will be going through that. Just give me 1 second. So the inductively coupled plasma atomic emission spectroscopy. This is coming very frequently in your exams. So what does it mean? So this is named either ICP AES or ICP OES. So it is either inductively coupled plasma atomic emission spectroscopy or inductively coupled plasma optical emission spectroscopy. It involves the excitation and de-excitation processes for electrons by absorption of radiation. And when the electron emits the electromagnetic radiation while coming back from an excited to de-excited state, the radiation is measured and it is analyzed, and it is called OES because of the optical property of the radiation during the de-excitation process. And because the spectral line has a definite wavelength, the AES spectroscopy is feasible. So this is what is happening, the absorption and the emission. So whenever it is coming back from the excited state, the emission is then recorded. So here we know that the flame photometric, that principle is being applied here as well. Flame in the atomic emission spectrometer, it transforms first the liquid samples into the vapor state. We have already seen that in flame photometry and AAS as well. And it decomposes the samples into simple molecules. Finally, these electrons, they are excited to higher energy levels and they return to the ground state by emission of radiation. And finally, on dispersion, the water or the solvent that is there, it is evaporated and only dry salt is left in the flame. On further heating at higher temperature, the dry salt is vaporized and the molecules are dissociated to neutral atoms which are responsible for the emission phenomena. And this vapor of neutral metal atoms is finally excited by the thermal energy of the flame. Now, a particular element, it emits characteristic spectra with a definite wavelength, and usually line spectra is obtained from atoms or ions, while molecules, they give band spectra. Okay, line spectra is obtained from atoms or ions, while the molecules are giving band spectra. So the emission spectra, it has a pressure regulator and a flow meter. It has an atomizer, a burner, an optical system, a photosensitive detector, and a recording output. So this is what the setup looks like. The flame atomic emission spectroscopy setup looks like this. There's a flame, there's a monochromator, there's a photocell, a detector and an amplifier, and finally a recorder. Now the atomizer, so the pressure regulator flow meter, they are usually just used for the proper adjustment. The atomizer is usually used to introduce a liquid sample into the flame at stable and reproducible rates. Glycerin is utilized as the solvent, and the burner is used for steady flame. And there's a deep metal grid across the mouth of the burner, so the flame is not fluctuating or striking back. And the optical system functions as a collector and monochromator of the light, and it is focused on the photosensitive detector. And the monochromator can isolate the characteristic electromagnetic radiation. Usually you have known this from the previous classes. So here the ICP-AES system has two basic parts: the inductively coupled plasma source and the atomic emission spectrometry detector. Now the source is very important. It is extremely hot and produces a maximum temperature of up to 66,500 degrees Kelvin, and this is enough for the ionization of samples. And the ICP source also comprises of three concentric uh, silica quartz tubes, each of which is open at the top. Now, a lot of questions is there about argon. So, what is the role of the argon gas? The argon stream carries the sample in form of an aerosol and passes through the central tube. And the excitation is provided by the radio frequency range radiations. When the argon gas is ionized in the intense electromagnetic field, it flows in a particular rotationally symmetrical pattern towards the magnetic field of the RF coil, and a stable high temperature plasma of about 7,000 Kelvin is then generated as a result of the inelastic collisions created between the neutral argon atoms and the charged particles. So this entire these points can be used for writing the answers of how the sources are working and why argon gas is used for the source, and what is the role of argon gas in the particular ICP torch. So now the pump is delivering the sample into the nebulizer. It is changed into mist and then it is introduced inside the plasma flame. Now the inelastic collisions are taking place in the plasma. Sample, when it is introduced, it is also colliding with the electrons and the charged ions in the plasma, and is also broken down into charged ions. Now, the various molecules break up into the respective atoms, which then lose electrons and recombine repeatedly in the plasma, giving off radiation at the characteristic wavelength of the elements involved. So, because of the low temperatures in a flame based system, not all of the atoms or elements present in the sample are excited, particularly if they exist in a polyatomic compound. But in AES, the atomic species can be created excited to larger temperatures as well, and thereby lots of atoms or elements can be excited. We have already seen what are the applications of flame photometry. Like they can be used for quantitative and qualitative, and they are characteristic to the particular metal. And with this, we can detect the presence of any specific element in the given sample as well. These presence is critical for the soil health. So for the flame test also, we can take some soil sample and we can determine the presence of various alkali and alkaline earth metals, and if anything in if any deficiency is there, then the soil can be supplied with specific fertilizer. Now the concentrations of sodium and potassium ions, they are very important in the human body for conducting various metabolic functions, and their concentrations can be determined by diluting and aspirating blood serum sample into the flame. So soft drinks, fruit juices, alcoholic beverages, they can also be analyzed by using flame photometry to determine the concentrations of various metals and elements. And they can also be used in determination of calcium and magnesium in cement. They can be used in determination of lead in petrol. And in particular, the ICP-AES system in agriculture, the ICP-AES technique can be used for analysis of agricultural and food products. In earth science, it can be used for the analysis of rare earth elements present in rocks. And trace metals from alloys, steel, lubricating oils, and gasoline can be analyzed by the ICP-AES technique. Similarly, in biology, aluminium from blood, copper from the brain, selenium in the liver, and sodium from breast milk can also be analyzed by the ICP-AES technique. And also trace elements like calcium, copper, iron, manganese, magnesium, phosphorus, potassium, and zinc from beer or wine can also be analyzed by the inductively coupled plasma atomic emission spectroscope. So these are mostly about the applications of the spectroscopy. I'll want to show you some diagrams regarding the setups. So lots of data is there regarding the plasma sources. So just let me show that. Just one second. So we have already just discussed about the plasma sources. So why plasma is required? Okay, why is it important? So also because they have a wide dynamic range, because they can permit simultaneous multi-element analysis, and many elements tend to form refractory compounds that are highly resistant to thermal decomposition. So only plasma can have a significant amount of cations and electrons under very high temperatures that can lead to increased atomization and excitation. So that is why plasma sources are used. And argon is used because these kind of plasmas involving argon, they can achieve very high temperatures greater than 7000 K. Okay, and here is how the torch looks like. So the torch had come, the component of the torch had come in your exam question. So here is the ICP torch. So this is how the concentration is there. So it contains three concentric quartz tubes through which the streams of argon gas are following. Okay, plasma gas flow is there, the auxiliary gas flow is there, and there's the tangential flow. And the outer tube is surrounded by a radio frequency powered induction coil. And the ionization of the flowing argon is achieved by a spark. So it interacts with a strong magnetic field and is forced to move in the vicinity of the magnetic of the induction coil at a very high speed, and the high temperature is also obtained. And at the top of the quartz tube, it experiences very high temperatures, and this can be accomplished by passing the argon tangentially around the walls of the tube. So in cases of liquid, this is how you can analyze the sample. So the liquid sample is there, it is passed to a pump where it is vaporized, and then it is introduced into the ICP torch. Okay, argon is passed to this nebulizer. Okay, it is converted here, and then it is going to the ICP torch where it is colliding with the atoms of the sample. This is in case of liquids. In case of solids, so if you have the ICP torch here, then argon is going from here, and you're introducing the sample here, where then it is first vaporized and then carried over to the ICP torch along with the argon flow. This is what the ICP flame looks like. Okay, this is what the torch looks like. So different components of the ICP torch also they have asked, different components of the flame. So from 6000 to very high temperatures at the core. So it looks like a flame, but from a region of 1 to 3 centimeter from the top of the tube, the plasma becomes transparent. So you will have a white core, that is the argon continuum line, and it is the highest temperature. And then there is a flame like tail, and then there's a transparent region at the very top. It's a transparent region, and there the measurements are made, and it is hotter than flame. It's almost 10,000 Kelvin. So the viewing region is around 6,000 degrees Celsius, which is about 1.5 to 2.5 centimeter above the top of the tube. And also argon is preferred because it is inert in nature. Okay, it is inert in nature for plasma torches and has few emission lines. It in itself, it has few emission lines and it is inert, so it can be used. And this can decrease the possibility of interferences with other analyte lines. So this is also an important point why argon is preferred as a plasma source. There is another kind of AES spectra which can be achieved with DCP. So that was ICP, inductively coupled plasma. This is direct current plasma. So this also you can have a read. So usually they require less argon, and but they have lower sensitivity than the ICP sources. So usually DCP is not much preferred, but still it is used. So this is the setup of a DCP, setup of a DCP AES. And then the comparison of DCP and ICP, if it is asked, you can write, but that it has the advantage of less argon consumption, has less spectral line interference and simpler instrumental requirements. But ICP sources, they are more sensitive and they are free from the frequent consumables and are also convenient to work with. So advantages of plasma sources. So this you can also write. They have minimum chemical interferences. They don't have oxide formation. Uniform temperature is measured. They're easily adaptable. There's no need for a separate lamp and no self absorption is required. And also laser induced plasmas. So LIBS is not there in your syllabus, but you can read this particular portion. I'll be giving out this PDF. So this you can read if you want to. This is not included. Plasma emission measurements, how the measurements are. So desirable properties of an emission spectrometer, this you can take these points for advantages of the spectrometers. Okay, advantages of the AES spectrometers, you can take that. So different kinds of monochromators also, it has been asked in one of the questions. Role of monochromators. So what kind of monochromators are that? Sequential monochromators are there, where the spectrometers, they are slowly scanned or rapidly scanned across blank regions. So what is the difference between normal monochromators and sequential monochromators? This can be a potential question. And many times polychromators are used, or which contain a series of photomultiplied tubes for detection. So they can use two-dimensional charge injection devices or charge coupled devices. So this can also be one of the points. So multi-channel instruments are not there in your syllabus, so you can just give it a miss. You can just read it through. And ICP torch positions, this one you can write. So if you have a longer path length, there is greater sensitivity. So that is why ICP torch positions are usually axial rather than radial. Okay, they are usually axial rather than radial. So you can, instead of these photographs, you can take the the schematic diagrams, and you can write this particular thing. Okay, axial position. This also you can write what are the benefits of AAS. So you can just take down these benefits versus disadvantages. So wherever you have to compare the AAS with AES, you can also include points of benefits and disadvantages in compared to ICP AES and ICP MS. This ICP OES also, what are the different quantitative advantages of ICP AES? You can write the benefits and the disadvantages here. So you can take down from this particular PDF, and you can also refer to your study material. So let me just see whether I've shared this particular point with you or not. I'm sharing some links. Okay, so whatever we have discussed regarding ICP AES and for ICP AES, the construction and the explanation of plasma sources, and the ICP torch and the disadvantages and advantages, I've just put it in the chat box. So you can copy that down. So from your various units, we have covered electronic spectra, the interaction of electromagnetic radiation. We covered that in the first class. We also covered a little bit of UV and visible spectrometry in the first class. Then in the second class, we went on to IR and NMR. So we covered IR, different applications. You have to pay attention to the wavelengths in which the various functional groups are absorbing, the kind of spectra. So you have seen the type of questions that have been discussed in class. So you can see the characteristic fingerprint regions. So different types of questions regarding IR and the construction that has been discussed. In NMR also, what is spin-spin splitting? This is important. The components of NMR spectrophotometry, the different kinds of factors affecting chemical shift, Okay, defined chemical shift, that has also been coming. Then in the third class we discussed about mass spectra also. So the different fragmentation patterns are important, the principles are important, and also what kinds of Mach Lafferty rearrangement can be possible for various species. They can even give you one type of an example and ask what is the fragmentation pattern. So such kinds of questions are regularly coming in the exam papers. Then we have gone on to fluorimeter and phosphorimeter. Many times these two techniques, they are being asked in comparison with each other. Intersystem crossing, internal conversion are popular questions. Jablonski diagram is a popular question. And the construction of the fluorescent spectrometers, these are coming. Then the applications of fluorimetry and phosphorimetry, this is also a very important question. So please refer to your study material for all these answers. Today we have also covered the other questions like quantum yield and fluorescence quenching and Stern-Volmer plots. Not too much in detail, but you will have to remember the expressions. You don't even have to derive it. The plots and the origin of the things, just understand and you remember. That will be sufficient for fluorimetry and phosphorimetry. Then, as regards to atomic spectra, you have AAS, you have AES, okay, and you also have flame photometry. So, the construction of the various components of the spectrophotometers, those are important. You also have atomic fluorescence spectrometry, that also we have covered. So, the advantages and disadvantages of all these techniques, the individual components, particularly the ICP torches, today we have discussed. Similarly, in AAS also we have different kinds of spectral interferences in all these spectrometers. Those are important. What kinds of spectral interferences are there? Sometimes these are so important that individual kind of spectral interferences are being asked in the questions. So you discuss how the samples are being introduced. What is the schematic? Draw a schematic diagram of the processes involved in flame photometry. So you have to go from the sample to how it is vaporized and how it is introduced. So those you have to see. In various kinds of spectrophotometry, have a general idea of what monochromators do, because monochromators are also coming in great detail in your exams. So for monochromators also you have to be careful. Sources, monochromators, what kind of detectors are there, justify why these are coming. And as regards to structure determination, the integrated problems are coming for IR, NMR, UV, and mass. So those problems we have discussed a few examples just yesterday. So you can just write. Yes, all other lecture materials, some of the presentations I had shared with Yash on Friday. So please ask him in the group if he has shared the materials, and the rest I have been sharing in the group. It's in the chat box itself. So I have been sharing all the links. So please go through the links, and please don't forget to share them in the group. So I hope you are doing that. So in the chat box, I have shared so many links in the classes, and if you have been paying attention, then you will be having access to all the links already. So share them in the group. Those who have not been attending classes also, they can also benefit. If they prefer to have self study, then they can just refer to these materials also, that which I have been sending in the group. So all the presentations have already been sent. And if you require any particular presentation or any particular help from me, then you can always contact me on my email ID. I have shared it before. I'm sending it again here, apramita.chand@gmail.com. Thank you, Divyendu, because you have said that all the materials provided in the chat box are shared in the group. Please ask Yash, if he's in the group, to share the PDFs. The PDFs and the presentations that I've done for the earlier classes, like for IR, UV, even for atomic absorption. Those presentations I had sent to him on email. So if you are not able to access those, or if you need some extra help also, you can contact me on this email asking for extra help. So that is all. I think we have completed your syllabus. We have gone through all the details. So we can just conclude the session. If anyone has any concluding remarks, you can just unmute yourselves and ask. Any doubts, any questions, any feedback, I'd be happy to answer. Okay, well, thank you. We have had a nice 7 days session covering different spectroscopic methods. I hope you had some interesting takeaways from the class, and I really hope that you'll be able to perform well. Thank you so much, Devendu. Thank you so much. And I am thankful to IGNU as well for giving me the opportunity to just interact with you all to take your classes. And I hope you do really well in the exams. And of course, if you face any kind of exam anxiety, also, you're welcome to contact me on mail. So I will be there to help you and to guide you as to how to write the exams. So thank you so much. And have a nice exam. All the best. Okay. Thank you. I'll be leaving the meeting now. Thank you so much.
Okay, thank you very much.
Thank you.
Good night, ma'am.
Good night.